Welcome back. In this video, you will learn about absolute and conditional convergence for series. Let's get to it. Alright, so far when we have been working with series, the majority of our tests for convergence required that the terms of the series we were testing to be positive. The one exception to this was the alternating series test, which allowed us to determine the convergence of a series whose terms alternated between being positive and negative. But what if we have a series that does have negative terms, but it doesn't alternate? For example, take a look at this series right here. We have the sum from n equals 1 to infinity of sine of n divided by n squared. This is a series for which the divergence test would be inconclusive for, and so we would be left to use some of our other convergence tests to determine if it converges or diverges. However, because of this sine of n in the numerator, not all of the terms of this series are going to be positive, right? Sine of n is going to be greater than or equal to -1 and less than or equal to +1. The sine function outputs values that oscillate between -1 and +1. And so many of the terms of this series will be negative terms, and so we can't use the majority of our convergence tests for this series. And it's also important to note that the terms of this series are not going to alternate back and forth between being positive and negative. We will have both positive and negative terms, but they're not going to switch every single term, right? The sine function will output a couple positive values in a row, and then it's going to switch to outputting a couple negative values, and then it's going to switch back to positive values, but it's not going to happen with every single term. It's going to take a couple terms for those signs to change. And so this series is not an alternating series, and so we can't use the alternating series test, which means that there's no convergence test that we currently know that will allow us to determine if this series converges or diverges. And so what we can do for a series like this is test for something that we call absolute convergence. And in infinite series, the sum of the terms of a sequence a sub n is absolutely convergent if the sum of the absolute value of a sub n converges. Alright, so what this is saying is that if we have a series that we want to determine the convergence of, what we can do is look at the series where we have the absolute value of a sub n, and if we can show that that series converges, then we can conclude that the original series is absolutely convergent. Okay, and so as a basic example, we'll come back to our series with sine in it later. Let's see if we can show that this alternating series right here is absolutely convergent. So what we will do is we will look at the series where we have the sum from n equals 1 to infinity of the absolute value of -1 to the power of n divided by n squared. Right? It's the same expression we have over here. We just put it inside absolute value bars. Now the absolute value of -1 to the power of n is just going to be 1, right? -1 to the power of n can only be one of two values. It'll either be -1 or +1, and the absolute value of -1 and +1 will be +1. So we could rewrite this series to be the sum from n equals 1 to infinity of 1 divided by n squared. Okay, the absolute value of n squared, of course, is just n squared, because anything squared is positive. Not to mention that our values of n are all positive, right? We're looking from n equals 1 to infinity, and so that denominator will always be positive. So we no longer need those absolute value bars. We now have this series, the sum from n equals 1 to infinity of 1 divided by n squared. And so this is our series where we have the absolute value of a sub n from our original series, and if we can show that this is a convergent series, then we can conclude that our original series is absolutely convergent. And so if we look at our series here, it looks like we have a p series, right? We have 1 divided by n raised to a power, and that power is 2. And so we have a p series where p is equal to 2, and since that is greater than 1, the p series converges. Right? If p was less than or equal to 1, then it would diverge instead, but since it's greater than 1, the p series converges. And so we've shown that this series converges, which means that our original series is absolutely convergent. And so we can write that down. This series is absolutely convergent. Okay, and so now we showed that this alternating series is absolutely convergent. And essentially what that means is that it doesn't matter if the terms of this series are all positive or if they are both positive and negative, it's going to converge either way. And so we would actually say that absolute convergence is stronger than regular convergence because it doesn't matter what the sign is for the terms of the series, it's going to converge either way. Okay, but now let's say we had a series with positive and negative terms that when we looked at the series of the absolute value of a sub n, that series was a divergent series instead of a convergent series like we had here. If that happened, we would not be able to conclude that our original series is absolutely convergent. We would have to make a different conclusion. And that conclusion is all dependent on the convergence of the original series. And so if you have an alternating series like we have right here, you would need to check to see if that alternating series is convergent or divergent by using the alternating series test. And based on the results of that test, we would either say that the series just flat out diverges or it converges, but it would be a different type of convergence known as conditionally convergent. And so next we're going to look at an example of a series that will be conditionally convergent. And essentially what that means is that that series will only be convergent if its terms are both positive and negative. If they are all positive, it's going to be divergent instead. And so let's take a look at an example of what I mean. So here we have the series, the sum from n equals 1 to infinity of negative 1 to the power of n divided by n. And so if we were to check to see if this series is absolutely convergent, we would want to take a look at the series where we have the sum from n equals 1 to infinity of the absolute value of negative 1 to the power of n divided by n. All right, now these absolute value bars are going to make negative 1 to the power of n become positive 1, so this will be equal to the sum from n equals 1 to infinity of 1 divided by n. Now we don't need absolute value bars around n because n is only defined for positive values, right? We have n equals 1 to infinity, so n is never going to be negative. And so this series right here, the sum from n equals 1 to infinity of 1 divided by n, is the series that represents the absolute value of a sub n from our original series. And so does this series converge or diverge? Well, maybe you recognize what this series is. It's the harmonic series, or a p series where p is equal to 1. And we know that when p is equal to 1, that the p series diverges. All right? Or maybe you just know that the harmonic series is a divergent series. Either way, this series is a divergent series, which means that our original series will not be absolutely convergent. However, it could be conditionally convergent if the original series itself converges. All right, and so in order to test that, since we have an alternating series, we will need to use the alternating series test. And remember, for the alternating series test, there are two requirements that need to be met in order for the alternating series to be convergent. The first requirement is that the limit as n approaches infinity of a sub n needs to be equal to 0, and the second requirement is that a sub n needs to be decreasing. And so if we look at our first requirement, we want to take the limit as n approaches infinity of a sub n, and remember, we exclude the part of our series that makes it an alternating series, so we're just going to look at 1 divided by n, not negative 1 to the power of n divided by n. We just remove that part, and now we have a sub n for the alternating series, and this limit needs to be equal to 0. And thankfully it is equal to 0. The limit as n approaches infinity of 1 divided by n will be 0 because a fixed value divided by infinity, or an increasing value because n is approaching infinity, will approach 0. All right, so this is equal to 0, and so our first requirement is met. And now our second requirement is that a sub n needs to be a decreasing sequence. In other words, a sub n plus 1 needs to be less than or equal to a sub n. The next term of the sequence needs to be less than or equal to the previous term. And so if we look at a sub n plus 1, that will be 1 divided by n plus 1, and a sub n is just 1 divided by n. All right, and so is it true that 1 divided by n plus 1 is less than or equal to 1 divided by n? Well, if you look at the denominators, we have n plus 1 and then just n. This denominator will always be 1 greater than this denominator, and when you have a larger denominator for a fraction, the value of that fraction will be smaller. And so, it is true that 1 divided by n plus 1 is less than or equal to 1 divided by n. That checks out, and so a sub n is a decreasing sequence, which means that both of our requirements were met, and so our alternating series converges. All right, and so we know that the sum from n equals 1 to infinity of negative 1 to the power of n divided by n converges, but the series where we had the absolute value of that sequence was divergent. And so because the original converges, but the series where we have the absolute value diverges, this series is not absolutely convergent. It is what we call conditionally convergent. It is only convergent when the terms can be both positive and negative. When all of the terms are positive, it instead diverges. And so our final conclusion here is that the sum from n equals 1 to infinity of negative 1 to the power of n divided by n conditionally converges. Okay, so yes, it does converge when its terms are both positive and negative, but when all of the terms are just positive, it diverges, and so it is conditionally convergent. And so that is a weaker type of convergence compared to absolute convergence, which is the strongest type of convergence. And so to summarize everything we just went over, this is what you need to know about absolute and conditional convergence. For an infinite series, where we have the sum of a sequence a sub n, that series will converge absolutely if both the original series and the series where we have the absolute value of a sub n converge. Right? If both of those converge, then our series converges absolutely. However, if the original series converges, but the series where you have the absolute value of a sub n diverges, then your series converges conditionally. And then if both of those series diverge, then of course you just have a divergent series. It doesn't converge at all. There are no conditions for which that series will be convergent. All right, and so just note that for absolute convergence, that you only need to show that the series for the absolute value of a sub n converges, because that will just automatically imply that the original converges as well. And so if the series for the absolute value of a sub n converges, your series is absolutely convergent. All right, but if that series diverges instead, you will then also need to check the convergence of the original series to determine if it is conditionally convergent or just flat out divergent. Okay, and so with that, let's look at a couple more examples of determining if a series is absolutely convergent or conditionally convergent. All right, so first up we have the series that we looked at the beginning of this lesson, where we have sine of n divided by n squared. I previously said that we could not determine the convergence of this series using any of our previous methods, but now we can determine if it converges or not by testing for absolute convergence. And so what we'll do is look at the series where we have the sum from n equals 1 to infinity of the absolute value of sine of n divided by n squared. All right, now there's not really anything to simplify here. We just now have a series that we want to determine the convergence of. And so since we have these absolute value bars, we now know that all of the terms of this series will be positive. And so that opens up the door to all of the other convergence tests that we previously learned how to use. And so just by looking at the structure of this particular series, I'm leaning towards using a comparison test because this is similar to a p-series, which we do know the convergence of. Right, we have some value divided by n raised to a power of 2, and so I'm thinking that we can compare this to the series where we have the sum from n equals 1 to infinity of 1 divided by n squared. All right, and specifically I'm thinking of using the direct comparison test, so I'm just going to make a note of that. So write that down here so we know which test we're using. And so when you use the direct comparison test, we first need to determine whether this comparison series converges or diverges. And this is a p-series where p is equal to 2. And so when you have a p-series where p is equal to 2, which is greater than 1, we know that the p-series converges. All right, when p is greater than 1, the series converges, but when it's less than or equal to 1, it diverges. All right, and so our comparison series converges, and so in order to determine that the series we're comparing it to also converges, we need to show that the terms of this series are greater than the terms of this series. Right, when your comparison series converges, that series needs to be greater than the series you're comparing it to. If it diverged, then it would need to be smaller. Those are the rules of the direct comparison test. And so what we need to show is that the absolute value of sine of n divided by n squared is less than or equal to 1 divided by n squared, right? 1 divided by n squared needs to be larger than this expression. And so would that be true for all values of n? Well, just comparing the two expressions, note that the denominators are the same. They're both n squared, and so that's not going to determine which is bigger. And so we need to look at the numerators, which are different. And so we have the absolute value of sine of n and 1. All right, now remember, sine of n, or the sine function, is always going to output a value between -1 and +1, right? Sine of n is greater than or equal to -1, but less than or equal to +1. However, if we're looking at the absolute value of sine of n, then all of those negative values will become positive. And so the absolute value of sine of n will be less than or equal to 1. This will never output any values that will be negative, and so we can just say that the absolute value of sine of n will be less than or equal to +1. All right, and that is exactly what we needed to be true for the numerators of these two expressions. The absolute value of sine of n is less than or equal to 1, which means that this statement is true. This expression will be less than or equal to this expression. All right, and so now we have shown that our comparison series, which converges, is greater than the series we are comparing it to, which means that that series also converges. And so what I can say is that this series also converges, and that is because of the direct comparison test. And since the series where we have the absolute value of a sub n from the original series converges, then we know that this original series is absolutely convergent. All right, and so that is going to be our final solution. We will say that the sum from n equals 1 to infinity of sine of n divided by n squared converges absolutely. All right, that is the final conclusion for this example. We were able to show that the series where we have the absolute value of a sub n for the original series converges, which means that the original series converges absolutely, or it's absolutely convergent. Okay, let's look at one more example for this video. All right, so finally we have this series, the sum from n equals 1 to infinity of -1 to the power of n plus 1 divided by the square root of n. Now right away I can tell that this is an alternating series because we have -1 to the power of n plus 1, and that part of the series will make the terms alternate between being positive and negative. And so what we can do, if we want to determine if this series converges absolutely, is look at the series where we have the sum from n equals 1 to infinity of the absolute value of -1 to the power of n plus 1 divided by the square root of n. All right, now the absolute value of -1 to the power of n plus 1 will just be positive 1, right? Because -1 to the power of n plus 1 is either going to be -1 or positive 1. So the absolute value of that will always be positive 1. And so this will be equal to the sum from n equals 1 to infinity of 1 divided by the square root of n. All right, and so that numerator just became 1, and in the denominator, we just have the square root of n, and remember that that output should always be positive. Okay, and so now we have a series that we can identify to be a p-series, right? We could rewrite this to be the sum from n equals 1 to infinity of 1 divided by n to the 1/2 power, because the square root is the same as taking that value to the 1/2 power. And so this is a p-series where we have 1 divided by n raised to a power of 1/2. And so p is equal to 1/2, which is less than 1, which means that this series diverges. All right, so the series where we have the absolute value of a sub n from our original series diverges, which means that this original series will not converge absolutely. Okay, so that's off the table, but it could converge conditionally. And so the way we will determine that is by testing our original series with a different test. Now in this case we have an alternating series because of this numerator of -1 to the power of n plus 1, and so we can test this series with another test. We can see if it converges or diverges from the alternating series test. And so if I clean up my work a little bit, let's work on the alternating series test here. Remember that there are two conditions that we need to check. The first one is that the limit as n approaches infinity of a sub n should be equal to 0. And the second one is that our sequence is decreasing. And remember that the sequence we are looking at for both of those requirements comes from our series, but it's not going to include the part that makes it alternating. All right, so instead of having -1 to the power of n plus 1 divided by the square root of n, we're just going to be looking at 1 divided by the square root of n. Okay, so for the first requirement, we need to check that the limit as n approaches infinity of a sub n, which will be 1 divided by the square root of n, is equal to 0. All right, now is that true for this limit? Well, as n approaches infinity, this denominator is going to get larger and larger. As n gets bigger, the square root of that number will also get bigger. And so we have a fixed value of 1 divided by an increasing denominator, or you could view it as just being infinity. And so that will approach 0 as n approaches infinity. And so this is equal to 0. So our first requirement is met. And then the second requirement is that the sequence is decreasing. And so we need to show that a sub n plus 1 is less than or equal to a sub n. The next term of the series is less than or equal to the previous term. And so a sub n plus 1 will be 1 divided by the square root of n plus 1, and a sub n is 1 divided by the square root of n. All right, so we just replaced n with n plus 1 for the n plus 1 term. And so is it true that this will be less than or equal to this term? Well, if you look at the denominators, since those are the only parts of these expressions that differ, we have the square root of n plus 1 and the square root of n. Since we're always going to have an additional value underneath the square root, we're taking the square root of a bigger number for this expression. And so that denominator will always be bigger than this denominator. And when you have a larger denominator for a fraction, the value of that fraction will be smaller. And so it is true that 1 divided by the square root of n plus 1 is less than or equal to 1 divided by the square root of n. A sub n plus 1 will be less than or equal to a sub n. And so we have shown that our series is decreasing, which means that both of our requirements are met for the alternating series test, which implies that our alternating series converges. Okay, so I'll write that down. We now know that this series converges from the alternating series test, but it diverges when we look at the absolute value of that series. And so, because the original series converges, but the absolute value series diverges, we can conclude that this series is conditionally convergent, or that it converges conditionally. It does not converge regardless of the signs of the terms. It only converges when we have both positive and negative terms. All right, when all of the terms are positive, it will diverge. And so our final answer is that the series, the sum from n equals 1 to infinity of -1 to the power of n plus 1 divided by the square root of n converges conditionally. Okay, that is the final solution. All right, so remember, when the absolute value of your series is convergent, then you know that your series is absolutely convergent, but if it diverges instead, then you need to go back to your original series and test it using some other test if you can, and if you find that that converges, then your series converges conditionally. If this series were to also diverge, meaning that the original diverges and the absolute value version diverges, then that series as a whole just diverges. Okay, and so that's what you need to know about absolute and conditional convergence for a series. And so with that, this was the last example for this lesson video, but if you want to see some more examples of determining absolute and conditional convergence, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.